So in this class we will take up a problem where shear force diagram is given and you are asked to find out the bending moment diagram. So given SFD shear force diagram, to find the load diagram and hence the bending moment diagram. So this is another type of problem which can be given in the examination. So in this problem, this is the shear force diagram which is given. All values are in kilonewtons. So load values are all given in kilonewtons. Now you can see here this AG is the length of the beam. The total length of the beam is 2 plus 2 plus 2 plus 3 plus 1, 10 meters. So these are the points A, B, C, D, E, F, G. These are the points where the values of shear forces are given, and he has given the profile of the shear force diagram also. So you can see that all are joined by straight lines. So from A to B, B to B it has got two values of shear force. Then it is horizontal, then downwards, then horizontal, then linearly decreasing, then upwards, then linearly decreasing. Now, when such a problem is given, you should have an idea about the profile of the shear force diagram. See here, you see here, shear force diagram, in earlier examples we have discussed that if we have two values of shear force at a point or a section in a beam, then definitely a point load may be there at that section, or it can have a reaction. So if the shear force diagram, if the arrow is downwards, if the shear force is decreasing, then there is a chance of having point load. If the shear force is increasing, then it is upwards, that is, there is a chance of having a reaction. So in this problem, at point C you can see that there is a decrease in shear force. It decreases from 6.357 to 0.357. That means there is a chance of point load at that point. And at the points B and F, if you see at B, shear force is increasing here from 2 to minus 2 to 6.357, and at F also it is changing from minus 8.6432 to plus 2. That means it is in the upward direction. That means reactions are possible there. So that means what you can say that this B and F were, so at B and F definitely you can have supports. So to write the load diagram, so load diagram means it is a diagram which represents the external loads acting on the beam including the span. Of course span is given here. Suppose if the shear force diagram is constant, it's a constant shear force, then it means that there is no load between those 2 points. Then if it is linearly decreasing like this, if the shear force diagram is linearly decreasing, then it represents a UDL. So that UDL intensity is given by whatever total load is acting divided by the span or the length over which that load is acting. So that gives the intensity. In this example, you can see that, you can see here from A to B it is linearly decreasing. That means there is a possibility of having UDL here. Then from D to F, then it is linearly decreasing. There is a possibility of having UDL. And F to G is also linearly decreasing. So that means UDL is there also. So then you at 3 portions you have got the UDL. Only thing is you have to find the intensity of that UDL. Then suppose if the shear force diagram is a parabola between any 2 points, then we can say that there is a triangle load or the UVL existing between those 2 points. Of course, in this example, there is no parabola, therefore there is no triangle load or UVL here. Now, let us see how we can find out the load diagram. So we have to concentrate on these points while you are writing the load diagram. So I will take from point to point. So now I will draw a line here. So I will mark the points A, B, C, D, E, F, G. I will mark the points. Now from A to B it is linearly decreasing. SFD is a linearly decreasing thing. Linearly decreasing means it is UDL. So then definitely there will be UDL from A to B. And what is the intensity of that UDL? Intensity is given by the total difference here. The total difference here, this is 2. You can see that total is 2. It is varying from 0 to minus 2. That means the total UDL acting from A to B is 2 and the span is 2 meters. Span is 2 meters. That means total load is 2 divided by span is 2 or length is 2. So you will get 1. 1 kilonewton per meter is the UDL acting from A to B. Next, at B, I will take at B. At B you can see that I have already told that B is a support now because there is shear force changes from -2 to plus 6.357. That means this total shear force, whatever is there here, that is nothing but your reaction. If 2 plus this, that means 8.357 kilonewton is the reaction here. So that gives the value of the reaction there. So at B, you have a reaction equal to 2 plus 6.357, that is 8.327 kilonewton. That means it is a support there. B is a support. Then from B to C, it is constant. Shear force is constant. It is called 6.357 only. That means there is no load. So no load between B and C. So you have to show a reaction here. UDL from A to B, reaction, then there is no load from B to C because shear force remains constant. Then at C, once again at C, you can see here, at C the shear force decreases from 6.357 to 0.357. That means the difference is 6 kilonewton. 6 kilonewton is a downward force. Shear force is decreasing. So downward force of 6 kilonewton is acting at C. So that we can show here. Then from C to D, once again shear force is constant. It is not varying. It is horizontal. Therefore there is no load from C to D. No load from C to D. Then from D to F. From D to F, we can see that it is linearly decreasing line. Linearly decreasing line means it is once again UDL. So what is the intensity of the UDL? Intensity of UDL is nothing but this total load. Total load is this 0.357 plus 8.643. So it comes out to be 9. So that 9 is the total load divided by span. Span is, that is length is 3 meters. From D to F it is 3 meters. So 9 divided by 3 kilonewton per meter is the UDL acting from D to F. Then at F you can see that shear force changes from minus 8.643 to plus 2. So this total will be now 10.643. So since it is acting upwards, we have to move like this. It is a reaction. 10.643 is a reaction. That means F is a support, simple support, where the reaction is 10.643. Next, from F to G, once again it is linearly decreasing line. Linearly decreasing line, UDL is present there. So the total UDL is this one. This is the total load. 2 minus 0, so it is 2. Span is 1 meter. So 2 by 1. So 2 kilonewton per meter is the UDL acting from F to G. So this is the load diagram. So this concept we have to note down for writing the load diagram. So from A to B, it is linearly decreasing. Therefore UDL. From B to C it is constant. Therefore no load. From C to at C, you have a downward value. That means the shear force decreases. Therefore, there is a point load. Then from C to D, it is constant. That means horizontal means there is no load. From D to F, linearly decreasing UDL. From F to G, linearly decreasing UDL. At F, it increases. Shear force increases. So reaction. So it is upward reaction. So this is how the load diagram is written. So once you write the load diagram, then you can draw the bending moment diagram as usual. So you have to calculate the bending moment at different points for this beam now. So only thing is here, there is one important observation here. Suppose if there is any external moment is acting on the beam, that cannot be represented. That cannot be represented in this load diagram because shear force diagram does not consider any external moment. So that is why, so I have written here external moment, if any, acting on the beam cannot be shown or cannot be represented. That is the only one drawback in this. So we assume that there is no external moment acting on the beam. Then only we can write the loading diagram. Now once we get this loading diagram, this is the loading diagram. So we can draw the bending moment diagram now. So from shear force diagram, first you have to draw the loading diagram. From the loading diagram, you have to get the bending moment diagram. Now as usual, this is the sign convention for calculating the bending moment. X-axis is the section under consideration. If you see left side or right side, irrespective of left or right, upward forces give positive bending moment, downward forces give negative bending moment, sagging and hogging as usual. So here, this is positive, this is negative. Okay. So we have to use the sign convention. Now we will move from the left end. This is a overhanging beam, doubly overhanging beam. AB and FG, they are the overhang portions. So on both sides you have the overhanging portion. Now bending moment at A will be 0, MA will be 0 because nothing is there to the left of A. MB, I am here now. So if you want to calculate the bending moment at B, see to the left side of B and calculate the bending moment. So to left side of B is downward force. So downward force gives negative bending moment. So minus UDL is 1 into 2 into, it acts at the midpoint, so 1 into 2 into 1. So it becomes 2 minus 2 kilonewton meter. Then bending moment at C, here at this point. See to the left side. So this is minus 1 into 2 into this distance. From C, distance to midpoint of UDL is 2 plus 1, 3. So minus 1 into 2 into 3. Then due to this reaction also we have to find out. So it is acting upwards. So bending moment is positive plus 8.357 into 2. So if you simplify that, you will get 10.714 kilonewton meter. Then come to point D. See to the left of D. Bending moment due to this downward force is minus 1 into 2 into distance from D is 2 plus 2 plus 1. Midpoint of this is 1. So 5. So minus 1 into 2 into 5 plus 8.357 into 4 meters. Distance from D is 4 meters minus bending moment into this 6 kilonewton is minus 6 into 2. So if you simplify that, you will get 11.48 kilonewton meter positive value. Then coming to point F, I will take then F. Afterwards we will find out at E. So coming to point F, so at F, see to the right side of F. So I am seeing to the right side of F. If you see to the right side of F, only you have this UDL. Only this UDL is there. It is acting downwards. Whether it is right side or left side, downward force gives negative bending moment. So it is minus 2 into 1 into 0.5. So this acts at the midpoint. So minus 2 into 1 into 0.5, which you are going to get as minus 1 kilonewton meter. And lastly, at the point G, bending moment is 0 because you see the right of G, no force is there, no moment is there, therefore it is 0. So now these are the values of bending moments. So you just plot the values now here. So at A it is 0, then at B it is minus 2. So below the line you have to show. Then at C it is 10.714 positive above the line. Then at D it is 11.48. At F it is minus 1. Then at G it is 0. Now one important thing is here. Here you can see here is the shear force diagram. Shear force is 0 at E. We can see here. It cuts this line at E. So at E, shear force is 0. So maximum bending moment occurs at the point where shear force is 0. This is very, very important. So maximum bending moment we have to calculate now. From the diagram, this is the given diagram, we can observe that at point E, shear force is 0. So let us take the distance E from this. Now I will take this portion, DF portion. I have written here. Now I am calculating the maximum bending moment where the shear force is 0. Then only that bending moment diagram is completed. So DF I have taken. So somewhere here E is there. I will take the distance of E from D as x. So this becomes 3 minus x because the distance from D to F is 3 meters. 3 minus x. And from similar triangles, what happens? This is 0.357 and this is 8.643. I have taken here. Now apply similar triangle principle. So 0.357 divided by x. So respective sides are proportional to each other. That should be equal to 8.643 divided by 3 minus x. So if you simplify this, if you solve this equation, you will get x as 0.113 meter. That means this point E lies at a distance of 0.113 meter from D. Now, since we know the distance of that E from D, 0.113 meter, now you can calculate the maximum bending moment at E. So, bending moment at E is M max. Now, to calculate that, what I have done here is, I have taken right side of E. Right side of E I have taken and I have written the diagram here. If you see the right side of E, what are all the things available from this point onwards? So, you have a UDL 3 kN per meter over a length of, what is that length? So, from D to E it is 0.113, from D to F it is 3. So, therefore, distance from E to F is 3 minus 0.113, which is 2.887 meter, and from F to G it is 1 meter. And you have a reaction here 10.643 kilonewton and another small UD at 2 kilonewton per meter from F to G. So this is the portion, these are the loads which are coming to the right of E. Now what I am doing is, I will consider this one and I will write the bending moment at E now. See, to the right side of E, so downward forces give negative bending moment, upward forces give positive bending moment. So, the 3 kN per meter is a downward force, minus 3 into 2.887 into it acts as midpoint of that. Okay, total load is 3 into 2.887 into it acts as the midpoint, that is 2.887 divided by 2. Then, bending moment due to this 10.643 kN reaction is positive because it is upwards, so plus 10.643 into distance is 2.887. Then this 2 kN per meter. So bending moment is downward force, bending moment is minus 2 into 1, that is the total UDL, into distance. Distance from here, distance from E to this 2 kN per meter is 2.887 plus 0.5. It is 3.387. See, this is negative, this is positive, this is negative. If you simplify this, you will get 11.45 kilonewton meter. This is the maximum bending moment. So that value also you have to plot here. 11.45. It is slightly more than this 11.425. Now, after that, you have to join the points. You should know the profile. Of course, here for bending moment diagram is parabola if it is UDL and it is a straight line if it is a concentrated load. So from A to B, we have all these points joined. Here we have all these points located. These points we have already located. Only F point E we have to mark it as 11.45. Now join these points now. From A to B it is parabola because UDL, B to C is a straight line, then C to D is a straight line, D to F is a parabola. Please note. Here, in between that D and F, you have E point. At E point, you have maximum bending moment. Maximum bending moment occurs at E 11.45. So then it decreases. It decreases and it is negative at F. So then another parabola from F to G because this is different UDL. So there are three parabolas here. From A to B one parabola, D to F another parabola, F to G another parabola. Rest of them are straight lines. So I have written here parabola A to B, D to F and F to G, remaining are straight lines. So this is how we can find out the bending moment diagram given shear force diagram. So in some question papers they have given this also. So only disadvantage is you cannot represent any external moment acting on the beam in such a case because shear force diagram does not imply any external moment acting on the beam. So here you can observe in this problem. So there are 2 points of contraflexion. So this is one point of contraflexion, this is another point of contraflexion. So where bending moment is 0. So here you can see that this is, suppose if you take this as M, this as N. So M and N, they are the points of contraflexion. If they ask you to find that, you can find, otherwise you can leave it. So in this problem, so shear force diagram is given. First you have to draw the loading diagram, then from the loading diagram you have to obtain the bending moment diagram as usual. So for getting the loading diagram, these are the steps you have to follow. By seeing the shear force diagram, So if there are two values of shear force, there is a possibility of point load or a reaction or a support. If there is constant shear force, there is no load acting between those 2 points. If the shear force diagram is linearly decreasing, there is a possibility of UDL acting over that length. Then if it's a parabola, then there is a chance of having UVL. So this is how you have to do the problem. Thank you.